Defining addition and multiplication on the natural numbers. Once we've defined the natural numbers with the Peano postulates, we explain what it means to add and multiply by using the following definitions. Definition. If n and m are natural numbers, then what does it mean to add 1 to a number? If you add 1 to a number, you get the successor of the number. You get the next number. Now this is a little bit complicated. If you add the successor of a number, you get the successor of adding the number. So adding 1 more than m to n gives you 1 more than n plus m. Not terribly crazy, but this alone together defines all of addition. For example, let's prove that 1 plus 1 is 2. Step 1, proof. We've used the Peano postulates earlier to prove that there are numbers 1 and 2, and that 2 is the successor of 1, the number that comes after 1. So, great. We've got 1 and 2, and we've defined what addition is. We know what equality is. We've got everything set up to prove that 1 plus 1 is 2. Well, by the definition, 1 plus 1, adding 1 gives you the successor of the first thing. So 1 plus 1 is the number that comes after 1, and the number that comes after 1 is 2. Therefore, 1 plus 1 is 2. We've proven it. Okay, let's try a harder one. Let's prove that 1 plus 2 is 3. Well, we've already defined 1, 2, and 3. 1 is the number that's given by postulate 1, 2 is the number that comes after 1, 3 is the number that comes after 2. So, 1 plus 2 is, 2 is the number that comes after 1, so we have 1 plus the number that comes after 1. Over here we say, if we add the number that comes after something, it's the number that comes after the two of those added together. So 1 plus the successor of 1 is 1 plus 1 successor. So this is 1 plus 1 successor by that definition, the second addition definition. And 1 plus 1 from the previous proposition is 2. And so we have the successor of 2, and the successor of 2 is 3, and so we are done. 1 plus 2 equals 3, quod erat demonstrandum. Anyway, in this fashion we can prove all of the basic addition facts. Do note that we needed to prove that 1 plus 1 was 2 in order to prove that 1 plus 2 is 3. We used it here. And we'll use 1 plus 2 equals 3 to prove that 1 plus 3 equals 4, and so on. For multiplication, we use the following definitions, not too different. Given any two numbers, when you multiply a number by 1, it doesn't change the number. When you multiply a number by 1 more than the number, well, you get n more than the two numbers multiplied together. So like 3 times 7 is 3 more than 3 times 6. That's basically what this is saying. And how do we use this? Again, to use these definitions to compute 3 times 4, we need to prove 3 times 3, which will require 3 times 2, which requires 3 times 1, which is just 3 by the very first multiplication axiom. So I'm not going to get into any examples of this, but hopefully you can at least, even though you wouldn't want to do this yourself, I understand you don't want to do this yourselves, you can at least appreciate how we are, in a really small amount of space, laying out an infinite number of situations with a very small number of fairly simple assumptions and definitions.